All right, so we start recording. We're going to start with presentations, and after that, I'm going to talk a little bit about the quiz as well. All right, so Swapnil, please go ahead.
Hello, everyone. So
could you hear the sound?
Yes.
Okay.
Today, me and my teammates Khushbu and Bashir were going to present this paper that was accepted at IEEE S&P. So the title of this paper is Plundervault, and it shows how you can inject faults into trusted execution environments using Intel SGX as a case study. So trusted execution environments, or TEEs, are being widely used to perform privacy preserving as well as secure computation. And as you can see in this slide, major computing hardware manufacturers have integrated TEEs into their processor architectures. The thing is, we take the guarantees put forth by these TEEs for granted, but RTE is actually secure. So in 2020, researchers showed that by undervolting Intel CPUs from the normal world, it is possible to induce faults inside the secure world, which is guarded by Intel's TE, namely the Intel Software Guard extensions. These can cause confidential data to be written into the secure memory or release private keys without even performing software attacks on the SGX. So you might think, like, how can we control the voltage of the CPU? Like, why is it so easy? Well, the same interface that gamers use to overclock their CPU allows one to underclock or undervolt their CPUs as well. And the reason this is possible is because modern CPUs use something known as dynamic frequency and voltage scaling. So you can control how much power your CPU is consuming by carefully modifying the voltage and in turn the clock frequency of the CPU. So this is done using a memory map register, which is known as hex 150. And using these registers, you can modify the clock frequency and voltage of Intel CPUs using any programs that are running in the normal world. And you will not need any special privilege to do this. Note that you cannot just undervolt Intel CPUs arbitrarily, as this is gonna lead to computer crashes. So there's a sweet spot in the CPU voltage frequency graph, as you can see in this slide, at which you can induce faults in the CPU without crashing it. So now let's look at a demo of how you can cause multiplication faults to be induced in the normal world through this undervolting concept. And I want you to pay careful attention to the XOR result, which you can see here, because when the XOR result has a bit flip, then that kind of signifies that a fault has occurred.
Most people assume that CPUs will return correct results, but this is only true if you run within specifications. We were able to inject faults into computations using software undervolting features on Intel processors. This is the same interface that gamers use for overclocking their computers. Watch as we slowly drop the voltage whilst running random multiplications. At an undervoltage value of 230 millivolts, we get an incorrect calculation. Investigating further, we see that a single bit was flipped in this wrong result.
So next, Bashir is gonna talk more about how this fault injection works in the secure world.
Thanks, Swapnil. So now that we know what Plundervault is and some of its core functionalities, let's talk about the threat model as well as some of its applications. So it's a standard Intel SGX adversary model where the attacker has full control over all of the software running outside of the enclave, including privileged system software such as the operating system and the BIOS. The adversary can't access the contents inside the SGX secure world, and the OS isn't trusted, but the adversary can access the MSR interface remotely, which is crucial for these attacks. And since only software accessible interfaces are exploited, attacks can be mounted without physical access to the target machine. So as we know, one of the things that we can do is faulting multiplication in the normal world, but we can also fault multiplication in the secure world by undervolting in the normal world. And as it turns out, the nature of the fault in the secure world, such as, for instance, bit flips, mimics that in the normal world. And we can use this towards inducing even larger faults with applications such as retrieving cryptographic keys. One good example of this is faulting the RSA using the Lenstra attack of 1996. The code that was used when testing Plundervault was Intel's specific example code for RSA, which employs the Chinese remainder theorem optimization, which happens to be susceptible to the Lenstra attack, which is a fault injection attack which requires a fault in exactly one of the two exponentiations of the core RSA operation. If we are unable to induce one of these faults, we are then able to retrieve an RSA private key. So what was done with Plundervolt was we kept undervolting at different voltage values and waiting for a multiplication fault before doing a decryption and then seeing if that decryption would also fault. As it turns out, we got the RSA error at the specific value of negative 240 millivolts. Once the error is produced, the Lenstra attack is able to be deployed, and as such, we are able to retrieve the RSA private key. Another thing we can fault is AES, specifically AES-NI or AES new instructions, which features 7 instructions introduced to improve speed and resistance to side channel attacks, and is used internally by SGX for operations such as sealing and unsealing enclave data. In this case, we actually don't wait for a multiplication fault. Instead, after undervolting, we randomly generate a platext, we encrypt it twice, and then we wait for a fault, specifically a single round fault. The fault is then used to generate an enclave key recovery attack. By repeating the operation enough times, the average happens to be 5, a fault can be generated in round 8, which happens to be the round where AES encryption's fault at, you guessed it, negative 240 millivolts, which can then be exploited in order to recover the full AES key.
Let's look at a calculation inside SGX. Watch as we run AES encryptions whilst undervolting. At minus 240 millivolts, the system is stable and doesn't crash. However, we were able to fault 2 AES encryptions inside SGX. Both these examples were in the 8th round, and that means that we can use the differential fault attack to find possible keys. If we cross-reference the 2 lists of keys, we find the actual AES encryption key. Let's check that with the source code. It matches. Using undervolting, we found the AES key in only a few minutes.
One last example we'll give is leaking private data by causing faults in pointer arithmetic. Pointer arithmetic for reads and writes actually employs multiplication when it's compiled. And as we know, we can fault multiplication by undervolting using Plundervolt. 2 specific scenarios were explored using this pointer arithmetic exploitation: faulting array index addresses and faulting memory allocation sizes. The former is what we use to leak private data. Specifically, as you'll soon see, causing an array index address fault will allow us to write private data that would usually be written in encrypted memory into untrusted memory, specifically user memory.
We already know that we can fault multiplications with undervolting, so what else can we do? If we look at this single line of C code, it compiles to an IMUL in assembly, and we know we can fault that. Let's look at a real example using SGX. Here we are performing multiple reads and writes inside the enclave, i.e. inside trusted memory. If we undervolt, we get a fault. Here you can see that the memory address produced is outside the enclave. Using undervolting, we were able to change a pointer address and write secret information to untrusted memory. Let's have a look at that secret information. And again, let's check the source code to prove we are correct. To summarise, in only a few minutes we have modified a pointer and written private information from inside the SGX enclave to untrusted memory, which could easily be read by an attacker.
So as you can see, there are a good number of faults that can be triggered using Plundervolt and subsequent attacks. I'll now hand it off to Khushbu, where she will provide further explanation.
Thanks, Bashir and Swapnil, for setting up the introduction, methodology, and evaluation. From here on, I'll discuss more about the severity of the attack the countermeasures proposed in the paper and the personal insights that we can derive from the paper. So in this slide, there is the experimentation phase of the paper. So they test their attack on different processors, which are all SGX enabled, starting from Skylake. And they also have access to multiple CPUs with the same model number. They show that even for those CPUs, there are slight differences that they encounter when undervolting. So each processor has slightly different voltage frequency graph, and the nature of the faults, however, still are the same. Now, I'll discuss the main results of the paper. So they are able to demonstrate that the integrity of SGX can be broken by undervolting the CPU. The authors further stress that undervolting is not exclusively a concern for cryptographic algorithms, and hence the sole reliance on fault-resistant cryptographic primitives is insufficient to protect against plundervolt adversaries at the software level. And therefore, the attack allows retrieval of RSA private keys, the retrieval of AES keys, and can also force the enclave to leak private data into the untrusted memory. Further, it can induce corruption in otherwise bug-free code. Now, moving ahead to some of the hardware and software countermeasures proposed in the paper against the plundervolt attack. As we go further, these countermeasures themselves have their limitations for implementation. So going ahead with the first countermeasure is to disable software voltage scaling altogether, which was also Intel's a solution as a mitigation strategy. However, it is not robust and it wasn't received well by the computer enthusiasts, as it does not address the root problem of plundervolt attack. This next is to disable software voltage scaling during the enclave operation. However, this adds additional overhead because of the time required to make the entry and exit from the enclave operations. The third is to limit the CPU voltage to known substantial values. However, every CPU die is different, and there are some constraints related to the age, frequency, and temperature, as they also play an important role. Further, the next mitigation strategy is multivariant enclave execution, which implies that the processors could execute enclaved computations twice in parallel on two different cores and halt once the execution diverges by leveraging the commodity hyperthreading features in Intel CPUs. However, this again leads to increase in computational overhead. So all of the hardware countermeasures proposed in the paper have their inherent limitations and challenges. Now, moving on to the software countermeasures proposed in the paper. First one of them is the use of fault-resistant cryptographic primitives, which require changes to the processor crypto APIs, and this again leads to substantial performance overhead. The next is application and compiler hardening. This needs manual checks at low level for every multiplication. However, the authors state that there are other high latency instructions also which may be faulted. The next is traditional memory safety hardening. This involves randomizing the enclave memory layout, but again, this does not address the root cause of the problem. So coming on to the insights and key takeaways that we can draw from the paper, the Intel's response of completely mitigating, disabling the MSR, that is the overclocking mailbox interface, corresponds to the recommended mitigation strategy outlined in the paper. However, it does not address the root cause for plundervolt. Also, there can be further avenues for fault injection through power and clocking management features, which might exist, and they have to be disabled separately. Also, the solutions provided by the authors in terms of the countermeasures for both hardware and software have their own set of challenges and thus are not very robust. Additionally, protecting SGX alone is insufficient, and entire computing infrastructure needs to be secured against external adversaries. Thanks.
Thank you, guys. Very dark, very dark times, right? Like, there's not much solutions for it, unfortunately. And
I mean, there are solutions, but like they each have their own disadvantages. And I think what we should do, like when trusting all this, TEs and stuff, instead of just focusing on, securing just our data. We should like focus on securing the entire company infrastructure. Like Tease is just one part. Like there's obviously the network component to it, the side channel component to it, and there are obviously other kinds of attacks as well. So instead of just focusing on making the T secure, we should also focus on the attack surface of the entire infrastructure we're using. So I think that's kind of the conclusion we reached.
Yeah, well, I mean, depends on how do you define secure, right? So you can, so the way that these guys usually, I mean, if you read the documentation about Tease, they very quickly, they say that we don't care about digital or physical side channels. So it's out of scope. And when you say that, then of course, then you can focus on other things. But the question is really, should we, put those things out of scope or not? And that's like very, very challenging question to answer. And it's the other problem is that yes, you can, for example, protect against physical side channels as well, but that comes at a cost, and not everybody wants to pay that cost, right? So that's another challenge. But yeah, I totally agree with your statement that the attack surface is important, and really what comes down to is having a generic and inclusive and diverse set of assumptions about the threat model, and try to address that. And if we can do that, then of course we will be much more secure. But that's the challenge for itself.
Yeah.
All right. So any questions, anybody in the audience about this? Yeah, it's kind of like, most of the papers we're going to read today, and I think you already read it. It's going to be about like, okay, we show that, keys are supposed to be secure, but then there's all sorts of, these other techniques that people can do in order to circumvent the assumptions that we have. So that's why I make the security very challenging these days. All right, so let's go to the next presenters. Who is next?
We.
All right. Do you have like a recorded video or?
Yeah, we have the recorded video. Yeah.
Is he also here?
Yeah.
Okay, cool. So yeah, so start sharing, please.
Okay. Can you see my screen?
Yes, we can.
Okay.
In our lecture, we have already had some basic understanding of hardware security. To dive into this topic, we need to start from the simple concept, the trusted execution environment. So what is T, the trusted execution environment? The comparison to T is called rich execution environment, where we will run our operating system and most of the software. However, operating platform is a much open platform which is vulnerable to malicious attack, such as sensitive private data, digital copyrights, and mobile payment. Around 2010, global platform came out T, which is used to verify the credential of the operating system. Here is a brief overview of the T structure. Trusted application is a T-specific application with high security. Each trusted application has one or several client app in the RE, which it can call the API from the client application, execute in T, and return the result. Other components such as T communication agents, T internal core API, trusted device drivers, and the shared memory are prepared for the cooperation of rich execution environments and the trusted execution environments. In short, the client application first calls the T client API to trigger the system call, enters the operating system kernel state of the reaching execution environment, and finds the corresponding driver according to the parameters of the call. The rich execution environment driver enters the monitor mode by calling the instructions and switches the processor to the safe kernel state to enter the security mode. After switching into the trusted environment, the service request of a client application is transmitted to the T side through the bus. Then into the trusted environment, it calls the corresponding trusted applications through the internal API. And finally, the trusted application returns the client applications, go back to the T kernel state, and then go back to the re environment. To understand Keystone better, we need to understand the concept of Enclave and one of its important commercial platform, Intel SGX. Enclave can be considered as the programs running inside of the trusted execution environment. It can be programmed inside of the T, and it can run on supported environment. For example, someone has an Enclave program and he wants to run it on remote computer with full data integrity and credentials. As a commercial T platform, Intel CPU includes such hardware SGX, short for safeguard software safeguard extension. The most straightforward way to do this is Intel SGX generates a pair of public-private key pairs for each SGX CPU to write the private keys onto chips during the manufacturing, as well as the public key certification center, also called certificate authority. And this is associated with each SGX CPU. The purpose is to provide public key authentication so people can confirm that it holds or use a public key belongs to the any specific group or individual. After these conditions are available, the Enclave program generates a hash summary based on the file information, and then it queries for the SGX CPU digital signature, and then sends the signature and the hash summary together to the end user. After the end user receives it, it uses the attestation service provided by Intel to verify the data sent from the Enclave. Currently, commercial platform provides inflexible threat models. For example, Intel SGX requires expensive memory encryption on memory protection system. ARM's Trustzone, however, uses software and hardware to provide the inferior modular T. A Trustzone T implementing multiple enclaves requires the memory management unit for further isolation. This fundamentally limits what operations enclaves can be allowed to perform and limits the enclaves to the user mode. The limitation naturally constrains all T systems built using the Trustzone as a base. Furthermore, there are many found gaps and hardware vulnerabilities inside of those commercial platforms. The new Keystone is based on the RISC-V. This is the first full-stack open source enclave with minimal requirements, and it requires isolation only with the standard RISC-V primitives. The core part of the Keystone is about security monitor and the physical memory protection. The open source platform provides a great community, also provides a great community for people with similar problems. This figure shows the minimum requirements for the Keystone to operate. It only requires a standard core as long as it supports RISC-V physical memory protection. It has three privilege modes: user mode, supervision mode, and the manager mode. If it needs to protect the memory from the untrusted devices, you need extra gasket physical memory protection. Also, we need a root of trust, which mostly a crypto engine to measure and sign the security monitor. It is also used as a platform to store keys. It can also be equipped with memory encryption part for the untrusted DRAM. For the overview of the Keystone, it has three privilege modes. Keystone Security Monitor mode is the core part. It manages enclaves and the physical memory protection entries. It also synchronizes physical memory protection configuration over multiple cores. It also handles remote attestation. Root of trust is stored in tamper-proof hardware to verify and check the security monitor so that the overall M mode can be trusted. The operating system is executed on top of the M mode in the S mode. The operating system can allocate memory and the interface, and so the user, security monitor can initialize the enclave. The operating system part, along with the untrusted app hosting an enclave, is the untrusted part of the keystone. The security monitor in the M mode can generate a trusted isolation for the enclave application to be executed. Here is a recap of Keystone workflow. We connect, if we want to connect a remote machine that runs a normal operating system, there are some user processes on top of the Keystone security monitor. The security monitor will control the physical memory protection that generates the enclave at isolated environment. The root of trust will provide the trust certificate to security monitor. Next, Ryan will talk about the evaluation part of the Keystone project.
Okay, thank you. I'm going to talk about the evaluation part of this paper. The first goal is to find out, is the Keystone framework viable in different applications? The second goal is to find how much overhead do the Keystone tease at a time. And the result is got by running 3 case studies and comparing their performance to benchmarks. Next slide, please. So before discussing the process, let me introduce the settings first. The security monitor is implemented by a system called Berkeley Boot Loader. The Berkeley Boot Loader, aka BBL, is a supervisor execution environment for risk systems. It can handle any illegal instructions that the risk processor is not equipped to handle directly in hardware. Also, it can handle responding to timer interrupts and unaligned memory access. And the REST2 runtime is implemented by C programming. Next slide, please. Let me talk about the lines of code in Security Monitor and the E-Rate runtime. The upper section is for the required components, and the lower section is for the optional components. Most of the modifications may not change the codes of Security Monitor, but affect the runtime part. The calculation is made using the command unifdef. It is used to remove ifdef lines from a file. This is an example of unidef. It means reading the file named original.c and remove ifdef a lines. After removing, the output is placed in the modified.c file. Next slide, please. The evaluation used 4 benchmarks. The first one is BIPS, and it is used for the energy consumption. The second one is a core mark. It can test the functionality of the processor core. The third and the fourth are RV8 and IOZoom, which are used for the binary translation engine and the optimal packet size. In the first 3 benchmarks, the overhead is less than 0.7%. This graph shows the IOZoom throughput in Keystone. There are 2 observations from the graph. In the writer, the highest throughput for the baseline is close to 500K, and in the reader, the highest is over 500K, and the throughput decreases as the file size increases. The second observation is that with the Keystone, there is a huge difference in the throughput, which means the throughput loss is high in IOZoom, and this implies that there exists large overhead. Next slide, please. Okay, Let's move to the case study part of the evaluation. The first case is about the security machine learning interference with Torch and E-Ray. The Torch is an open source machine learning library and a script language based on the Lua programming language. And it includes a wide range of algorithms for deep learning. This case study includes 9 Torch-based models and conducts 2 experiments. One is about the static aspect, and the other is about the dynamic. For both the static and dynamic, the overhead are relatively high, which is close to 10%. Next slide, please. The second case study is using fast artificial neural network and CL4. The FAN is a cross-platform open source programming library that is used for developing multiple layer feed-forward artificial neural networks. In this case, FAN and CL4 are used for train and test in a sample XO. The logic of XO is shown in this graph. The overhead in this case increases 0.36%. Next slide, please. The third case study is to implement a secure server application to count words by using E-Ray and Security Monitor. The Keystone takes 45,000 cycles for a round trip with an empty message, secure channel, and the message passing overheads. Also, it takes 2,000 more cycles if there is a new message. Next slide, please. To conclude, the Keystone first solves the customization problem of formalities. Also, based on the result from the evaluation, the Keystone is viable in different configurations for real applications. Finally, this Keystone provides a great framework for future T research and novel T designs. Thank you for watching.
All right, thank you. Any questions here? Yeah, Keystone is, I mean, if you guys want to play with T's code and implementation, they have a pretty decent GitHub repo. It's one of, I mean, REST-WAV is like getting much more and more traction these days as an open source ISA. And there are lots of works on adding different components for the ISA, and Keystone is actually one of those projects also coming out of Berkeley, which is trying to add, you know, a formalized version for trusted execution environment, basically. So yeah, if you're interested to know more, you can check out their website and learn about their tutorials and stuff like that. All right, any questions? Okay, so next we have Wei Chen, Harry, Kaiwan. Any of you guys here? I think Kaiwan, I see it here.
Yes.
And Harry is here. Okay. So who's gonna share screen?
I'll start sharing screen, Professor. So.
Okay. So why don't you start sharing, but let's have like maybe a 2-3 minute break and then we can start.
Okay.
All right.
Okay.
Yeah. Cool. All right. Harry, are you there?
Yes.
Yeah, please go ahead.
Okay. Hello everyone. My name is Kaiwan and I present with my teammates Harry and Willie. Today we are going to present the paper DeepAttest, an end-to-end attestation framework for deep neural networks. Next slide, please. Harry. Okay. In this paper, the major problem that the authors try to tackle is hardware-level intellectual property protection of the device providers for DN application. Since the customers might misuse the device for illegal or unauthorized DN application, the on-device attestation is needed to prevent illegal DN models from execution and detect malicious modification. The paper therefore proposed DeepAttest, an on-device DNN attestation scheme, which basically checked the legitimacy of an unknown deployed DNN and determine whether to continue the DNN evaluation or abort it. Specifically, deep attacks works by designing a device-specific fingerprint as an attestation criterion with the support of TEAS. And on-device attestation is required to achieve following goals: preserving the performance of the deployed DNN, providing reliable and secure attestation decision, low latency and power consumption to ensure applicability in real-time DNN applications, and resource-constrained systems. Next slide, please. So next, let's talk about the background. As the previous presentation has mentioned, T is usually provided by CPU hardware architecture to ensure secure execution of confidential application using program isolation. And the Intel SGX ARM Trustzone are the examples of T's. And existing security and inference methods can be divided into two categories: full execution inside the T and outsourcing partial computation from the T to untrusted environments. Fully T-based DNN evaluation is a naive way that basically runs all the computation inside T. But this way is obviously not feasible due to the limited secure memory. For example, the enclave memory size of Intel SGX is 128 megabytes, which is much smaller than the size of contemporary DL models. Besides the memory constraint, encryption and decryption for communicating data with secure memory create large overhead. On the other hand, outsource-based security and inference, which partitions DNN computation into nonlinear and linear operation. And then these two parts are assigned to the T and the untrusted environment for execution respectively. The table below shows the comparison between existing security and inference methods and deep attacks in terms of platform requirements, workload in T, resistance to offline-online data temper, and overhead. The two methods, fully T-based and outsource-based, can guarantee result integrity and protect the weight from online data temper. However, they are vulnerable to offline data temper, for example, fault injection, where the attackers modifies the data stored in the untrusted memory before it is used in a secure DNN inference. Unlike the previous methods, deep attacks can prevent both offline and online data temper and incur low overhead. This is because it uses T for only fingerprint key verification and provide the hybrid trigger mechanism to prevent data temper. And how the fingerprints generate and the attestation works will be discussed in a later presentation. Next slide, please. So threat model, and adversary might try to bypass the on-device attestation. And here are the three potential attacks based on different adversary levels. In the full DNN program substitution attack, the attackers is assumed to know the physical address of the deployed DNN model and attempts to substitute the original content with its unauthorized DNN model, trying to map his model to the device. Secondly, in fingerprint forgery attack, in order to pass the attestation, the attacker might try to forge the fingerprint key that's stored in secure memory by brute force searching. And the last one, fault injection, is a memory content modification attacks. The attackers are assumed to know the memory allocation of the target device and randomly modify memory blocks maliciously. And then I'll hand over to Harry and he will introduce the solutions.
So I'll continue with the algorithm for fingerprint generation. So starting off, we have the inputs, which is the pre-trained unmarked DNNs, like unmarked DNNs in the sense like the DNN that we kind of like to use. The second is the training data that we provide to the system. The third is the location of target layers, which is denoted by L, and the embedding dimension N, and the code length V. And like I guess like for now, the description of all these parameters will be put up in the consecutive slide. I'll just like enumerating them here so that we see what is happening. So this is the algorithm. This is just a 3-step algorithm, which involves like first step is key generation, second is fingerprint construction, and the third one is like you utilizing the results from first 2 steps to fine tune the model to actually embed your fingerprints into the DNN. And finally, you get the outputs, which is the marked DNNs and other deliverables from the algorithm. So just a hilarious piece which I thought was like because a paper which has like both code as well as algorithm explained detailed manner would be helpful for like naive people who are just getting started. So I guess like this is a good paper in that sense. So I just included this. So it does run well, and the algorithm is like explained so well, and the inputs are also like it has some example inputs being taken, and they just run through the entire algorithm and simulate how the input is getting transformed and fingerprint is getting generated. So this is the algorithm. So the first step of the key generation process is like you should have the device code book. What is the device code book? It's nothing but a matrix. How you can visualize that is like we will have, let's say for the system that we design, we will have a maximum of uses which is denoted by B maximum uses, and we will have a code length assigned to each such uses of length V. So this is a matrix of order or size V cross B. So and how do we generate this code book? It is randomly generated. So but the criteria is each column here is like a unique code vector. So it like sort of preserves the uniqueness among the several code vectors which is generated for distinct uses. And where it is stored inside the TEE so that it's kind of safe. It's not in the untrusted memory. So the second step is to generate an orthogonal matrix, which is key for any like a linear algebra transformation. So the columns of U are the basis vectors for fingerprint generation, which is denoted by FP. And the third one is the projection matrix. For each and every owner, we have the secret projection matrix X, whose size is given by V cross N. So it's basically code length V into the embedding dimension N, which is nothing but the dimension of the model that is under consideration that we kind of try to attest through this process. So again, this is also sample from a normal distribution, and N is like dimension of target layer. So how do we do this? It's just the simple math expression. So in the fingerprint construction, we use the code books vectors, column vectors, and the coefficient matrix for fingerprint is like constructed from this equation. So the Bij is generated from Cij, which is taken from the code book, and this is the equation through which we arrive at Bij, which is the coefficients which will be useful in fingerprint generation. And at last, like fingerprint is like crafted as the linear combination of basis vectors. So we use the basis vectors which is generated from the orthogonal matrix step, and we sort of multiply the coefficients generated, and we arrive at the fingerprints. So Fj denotes the fingerprints, which is the weighted sum of the basis vectors. So it spans the basis that is under consideration. So how do we use this? So we have the fingerprint now. How do we actually embed this into the model? This is how we do. So in general, the loss of a model would be given by the first term alone in the last expression in the slide, which is L0. But what we do here is we add this additional term which has this embedded fingerprint into it. So it's weighed by this gamma, and together with the conventional loss, both the losses are being incorporated into the model's training parameters. So this is how it happens. Since both the losses are like being minimized throughout the process, both criteria is like being met out. One is the model's objective function, and the second one is the fingerprint actually being embedded into the weight vectors. So so we have the DNN model. I mean the the actual model's weight vectors being embedded with the fingerprints. Okay, so is this useful? Is this enough? Should we stop at this point? We will look at this question in the consecutive slide. Just before that, as like Kaivan said, this algorithm like is useful both for online and offline algorithms. So like offline data tampering is also being prevented by this algorithm, and the online process is also like kind of being continuously monitored by this algorithm. And how it accomplishes this is by this two-step process. One is the static trigger. This signal is generated whenever OS detects a DNN program's request to run. So whenever a DNN program is kind of invoked, a signal is generated and it's kind of trapped and captured by the deep attest program, and it does the attestation process to let it run actually. This helps us to like do the offline data monitoring and make sure that the data is not tampered before we even start the process during the online mode. So the second one is the dynamic trigger, which is like quite useful for online mode. We have like two sources here. How do we actually what leads to a dynamic trigger? The first one is a memory chain signal, which is like monitored by the deep attest. It's a signal which is intrinsic to OS, and again the DNN program captures it. And the second one is the timestamp signal from the trusted timer within our container. So these two are the trigger mechanisms upon which we let our algorithm to run. So they basically cater to both offline and online stages. So this is the secure fingerprint detection mechanism. So we want to reconstruct our fingerprint. We already have like generated a fingerprint and embedded that into our DNN model. Now we are like going into the user's mode. The user is trying to use a DNN. We want to get the DNN model from the trusted execution unit TE memory into our memory for execution, and try to again do the generation mechanism. We generate the FP and compare it with the predefined FP that we already know. So, and what's special about this paper? One of the important considerations that we were like talking about was the TE size is one of the major factors for like exponentially large DNN models. Today's TE sizes are about 198 MB or so. If we are like trying to use some large models, it is not even possible to like import the entire model and do this computation. So what's so special with this algorithm which makes us do this? So this is it. So it's the intrinsic independence inside the algorithm that we will see in the later slide. What this algorithm does is it assumes it independently decodes each and every bit. So at any moment of time, it just needs like partial chunks of weight vectors into it. So it will just import part of the model, which is like good to reside inside a TE, which the TE can hold. And because of this partition the process, it can actually capture the memory can actually withstand the models like size. And the second is the parallelism that we can do because of the independent computations. We are like through this algorithm, we are like postulating that each and every bits decoding process is independent. So we can also incorporate parallelism and improve our latency. So that's what is the major power of this algorithm. So, and this is just the decoding part which runs online, which captures the fingerprint in the online mode to do the comparison to allow the DNN to run or about the mode. So yeah, this is just a question. I wanted to be a bit interactive. We have two keys here. If you press one key, you will be caught red-handed, and the second key you get all you ever wanted. So which one of these will you press? And like, does this even make sense? Like if you have two keys, what's the rate of your success? I mean, it's just a generic question. Okay, I will just go ahead. So it's just like 50-50 probability. So if we don't know actually which key is like is our key, or like which one is the original, I mean, here how we can like interpret this is one of this would be like embedded, would contain the embedded fingerprint, and the other one would be devoid of this fingerprint. So if you tamper the one which is devoid of fingerprint, we can like make any malicious DNN to run, because during online checking, it will just pass through. So this is a problem that we are going to deal with. We have weight vectors and we have embedded our fingerprints into the weight vectors. But if we think about the CPU's like memory map, we will have the weight vectors organized into like discrete chunks of data, let's say like sizes of n, and after that we have a gap which has like no weight vectors which are actually being embedded with fingerprints. So that is like sort of like completely agnostic to the algorithm. So what a malicious user who like under the threat models that we assumed before, if the user knows a complete memory map, he can just go ahead and pick the weight vectors which were like not being embedded with FP and just operate on it and let his own customized DNN to run, because that will just pass through the algorithm during the online mode because it doesn't have the FP embedded into it. So how do we do get away with this? What we can do is like we can shuffle the embedded vectors and the non-embedded vectors, so that whenever the user tries to embed in continuous segments, the probability of him tampering a weighted vector becomes like comparatively higher, so that while it goes to online mode, we can capture the tampering and we can sort of abort the process. So that is the major idea here. So we kind of take the weight vectors, shuffle it over the memory map to make sure that we are decreasing the probability of like attacker getting away with tampering our weight vectors. So this is another mechanism which makes this algorithm more robust. So that is the shredder process, which shuffles the weights and stores data in untrusted memory. And this also constructs a very robust mathematical model. It's a very interesting result which proposes that there is a there is a well-defined bound of what how much an attacker can succeed against this process. So that makes this algorithm even more attractive. So this is just some probabilistic Poisson process that is going on here. So the first expression denotes the probability of malicious user tampering a segment of memory, which is denoted by S. To successfully insert a single segment, an adversary has to like stay away from the weight vectors which were embedded and only insert into like non fingerprint embedded vectors. So in order to do so, he has to like make use of the largest available weight vectors possible, but that success rate is given by this probabilistic expression. And the plot of this is shown on the right hand side, which is like very intuitive. It's kind of 3D. If you look at it, the graph is 2D, but it has 3 parameters. The independent parameter is the injection ratio. What injection ratio basically tells us the ratio of the marked weight vectors, which is the weight vectors which contain FP, to the weight to the ratio of like the whole weight vectors which do not have the FP. So it's like how much you are marking, or like how much amount of computation you are performing, that much amount of like success rate of the attacker you can subside. So if you mark a major chunk of the weight vectors, you're sure that the attacker is going to like disturb one of your weight vectors, and that is going to get caught during the online process. So it's it shows that trade-off. On the top, you can see that the red curves has like lower attack success rate, 0.1. This is because he has marked a higher rate, 0.45. Whereas for the blue curve on the y-axis, it's just 0.3. So you have a higher attacker success rate. So the attacker can comparatively get with this algorithm easily. So yep. So this is what I get out of this course. So I mean, T inside your device which receives OTP from bank. I mean, as soon as you do some secure transactions, I guess there is a NS bit which toggles this into the secure mode, and everything happens within TE. And this is how I interpret it. Like, I appreciate this course after studying this. There's so much of research that goes beneath all the things that needs to happen securely. And that side of the bank, I'm not sure what is happening. So this is the customized attestation interval discussion. So this potentially says how the algorithm is like kind of being implemented. So we previously looked at the algorithm is kind of parallelized because of the independence that is given by the data set. We can actually decode each and every bit independently. That means we can take some groups of bits, take that into the memory, and independently operate on them in a parallel fashion, decrease the latency. After you are done with those chunk of bits, you can throw them out and you can bring in the next chunk of bits. So your memory is saving and your latency is also like kind of decreasing. So that is a win-win situation here. So yeah, the 2 points which I mentioned, which is the data pipeline here. We have two pipeline threads. One is the memory copy, which copies discrete chunks of bits into your memory just to like do the fingerprint checking and comparison to let it run or abort the system. And like after the computation is done, it's moved outside. And the early termination is kind of a break statement, which like comes out of the system as soon as you observe something malicious happening. So I believe we'll go ahead with the evaluation. So.
Yep. All right. Thank you, Harry. So now we will move on to some evaluation done by the authors. So there are actually a lot of different experiments shown in the paper. They have compared a bunch of different metrics like latency, throughput, model size, embedding the fingerprint to the fully connected layer versus embedding the fingerprint to the convolutional layers. And they have also evaluations on the integrity, the efficiency, scalability, etc. We kind of don't have time to go through them all, so I'm just gonna focus on a few that looks pretty interesting to us. So DEPA test was actually tested on the 4 benchmarks that's shown here. We have models that are small and one that's pretty large, the VGG16, which is 270 megabytes. And so the last column here actually shows the marked layer size. So the marked layer size is actually the layer that holds the embedded fingerprint. So this is kind of the reason why the latency was improved so much and why DEPA test was able to run models that are very large, because they only have to transfer or copy the weights, which is only about 10% to the secure memory in T. And the next thing that also needs to be not yet. Yeah. So the next thing that needs to be verified is
either I think, did your voice break up or is my internet is not working? Because for some time you were frozen.
Oh, is it working now?
Yeah, it is working now.
Oh, all right.
Maybe it was on my side. Sorry. Go ahead.
So the next thing that we'll be interested in is the fidelity. So the fidelity means that because we're actually modifying the model when we are embedding the weights. So we want to make sure that after embedding the weights, the model does not break or it gets corrupted. Yeah, so as you can see down here, this is actually the test accuracy. And after marking the model with the fingerprint, using the loss function shown down here, you can see that the test accuracy does not drop and some even improved. So the reason why some improves is because during the refinement process, the refinement training process, we added this regularization term to the loss function, which is in this red rectangle here, and would be able to prevent the model from overfitting. So that's why the test accuracy sometimes gets a little bit higher than the baseline model. So yeah, this shows that DEPA test has the high fidelity. So yeah, next slide, please. And another thing that we were interested in is the reliability. So reliability here just means that they want to make sure when there is unauthenticated programs, unauthentic programs are not allowed for execution. So this is like when there's an unmarked program that wants to overuse the device, or when there is a full injection on a legitimate model. So checking the reliability is equivalent to checking the bit error rate, which is BER here. I think this was not introduced previously. So basically how the attestation process works is that they will compare the fingerprint with the one that's previously stored in the secure memory. And if the difference or the bit error rate of the fingerprint is 0, then the attestation will pass. So that's why reliability is equivalent to checking whether the model is able to yield a 0-bit error rate. So what they did is that they injected noise to the weights that holds the fingerprint, and then experiment on whether the bit error rate is 0. So as you can see, from the figure down here, only when the noise, the standard deviation of the noise and the range of the noise is 0, the bit error rate would be 0. So this just means that the framework is very sensitive to unintended modification and is very robust against fault injection. Yeah, so next slide, please. So the last thing would be the performance comparison with the two similar works. So DEPA test at the black here. So you can see that the latency then the throughput also is also about the same. And yeah, the reason is just because they do not need to transfer like the entire model to the secure memory in T. Next slide, please. Yeah, so the conclusion is, so we have introduced DEPA test. It's a framework with algorithm, software, hardware co-design. The fingerprint generation attestation is the algorithm part. And as Harry have introduced earlier, the shared storage mechanism is able to prevent fault injection. And this framework also gives user the freedom to specify their own needs. They will be able to perform trade-off between security level and attestation overhead by like making their own configuration according to their own requirements. So I think this is kind of also why they say that DEPA test has generalizability. Yeah, and that pretty much concludes our presentation.
All right, thank you. Any questions, anybody? All right, certainly, well, it was a pretty detailed presentation. But yeah, that's certainly very interesting. Yeah, the idea is slightly different than what we have seen before. So it's not really trying to protect data, but it's trying to protect IP in some sense, and that's also can be important in some cases. Yeah. All right. So the last presentation. We have Wang Ji and Spencer.
Yep, we're here.
Okay, cool. Please go ahead whenever you're ready. We can't hear anything. I think you didn't share your the sound with your when you were sharing. Or can you hear it yourself?
Yeah, Wang Ji, I think you need to share the audio.
So sorry, I will share it again. Hello, today we are going to talk about FTPM, a software-only implementation of a TPM chip. Here is the outline of our presentation. We are going to talk about first motivation, then TPM overview, ARM trust zone and the limitations, high-level architecture and threat model, overcoming trust zone shortcomings, hardware requirements, design compromises, TPM 2.0 features, performance evaluation, and finally, analysis and conclusion. First, I will discuss the motivation of this paper. The current CPU architectures, such as ARM and Intel CPUs, have started to offer trusted computing features in their CPUs, aimed at displacing dedicated trusted hardware. Unfortunately, these CPU architectures raise serious challenges to build trusted systems because they omit providing secure resources outside the CPU parameter. Therefore, this paper implemented a software-only trusted platform module using ARM TrustZoom. They have found 3 approaches to overcome the limitations of ARM TrustZoom. I will talk about it later. This paper also addresses security analysis between FTPM and TPM chips. Let's have an overview of Trusted Platform Module. TPMs provide a small set of primitives that can offer a high degree of security assurance. It offers strong machine identity. It can prevent malicious software rollbacks, protect data encryption keys, and testing the mode of a device. TPM-based secure system can very commonly used in industry. For example, in Microsoft, modern version of Windows OS use TPMs to offer features such as BitLocker disk encryption, virtual smart cards, early launch anti-malware, and key and device health attestation. In Google, Chrome OS use TPMs for a variety of tasks, including software and firmware rollback prevention, protecting user data encryption keys, and testing the mode of a device. The research community has proposed many uses for TPMs in recent years. They have discussed like secure virtual machine for the cloud, secure applications, OS and hyperversion, and other novel secure functionality. To see the history of TPM, it goes from 0.1 version, 1.0 version to 2.0 version. In late 1999, the TCPA is formed, and in 2001, the TPM 1.0 is released until 2014, the TPM 2.0 appears. Recognizing the increasing demand for security, modern CPUs have started to incorporate trusted computing features, such as ARM TrustZoom. ARM TrustZoom is ARM's hardware support for trusted computing. It is a set of security extensions found in many recent ARM processors. The software stack can switch between the 2 states, referred to as worlds, normal world and secure world. Each world acts as a runtime environment with its own resources. There are some ARM features I want to discuss. First, the secure monitor. It is an ARM processor mode that enables context switching between the secure and the normal worlds. A special register determines whether the processor core runs code in the secure or non-secure worlds. When the core runs in monitor mode, the processor is considered secure regardless of the value of the register. The second feature is the secure world entry and exit. By design, an ARM platform always boosts into the secure world first. The normal world uses a special ARM instruction called secure monitor call to transfer control into the secure world. When the CPU executes the SMC instruction, the hardware switches into the secure monitor, which performs a secure context switch into the secure world. Hardware interrupts can trap directly into the secure monitor code, which enables flexible routing of those interrupts to either world. This allows I/O devices to map their interrupts to the secure world if desired. The third feature is curtain memory. At boot time, the software running in the secure monitor can allocate a range of physical addresses to the secure world only, creating the abstraction of curtain memory. It is the memory inaccessible to the rest of the system. For this, ARM adds an extra control signal for each of the reading and the write channels on the main memory bus. There are still several shortcomings of ARM TrustZone. First, there is no trusted storage. The ARM TrustZone specification offers no guidelines on how to implement secure storage for TrustZone. The lack of secure storage drastically reduced the effectiveness of TrustZone as trusted computing hardware. Second, ARM TrustZone lack of secure entropy and persistent counters. The TrustZone specification is silent on offering a secure entropy source or a monotonically increasing persistent counter. Third, ARM TrustZone lack of virtualization. Although ARM offers virtualization extensions, the ARM TrustZone specification does not mandate it. As a result, many ARM-based SoCs used in mobile devices today lack virtualization support. Fourth, ARM TrustZone lack of secure clock and other peripherals. And at last, ARM TrustZone lack of access. Most SoC hardware vendors do not provide access to their firmware. As a result, many developers and researchers are unable to find ways to deploy their system or prototypes to TrustZone. In order to solve the limitations of ARM TrustZone, the paper implements a trusted execution environment that acts as a basic operating system for the secure world. This figure illustrates the architecture. At a higher level, the TE consists of a monitor, a dispatcher, and a runtime, where one or more trusted services, such as the FTPM, can run one at a time. The TE exposes a single trusted service interface to the normal world using shared memory. By leveraging the isolation properties of ARM TrustZone, the TE provides shielded execution, a term coined by previous work. With shielded execution, the TE offers two security guarantees: confidentiality and integrity. This means the whole execution of the FTPM is hidden from the rest of the system, and the operating system cannot affect the behavior of the FTPM. A primary assumption is that the commodity OS running in the normal world is untrusted and potentially compromised. This OS could mount various attacks to code running in TrustZone, such as making invalid calls to TrustZone, not responding to requests coming from TrustZone, or responding incorrectly. In handling these attacks, it is important to distinguish between two cases: not handling or answering TrustZone's requests or acting maliciously. The first class of attacks corresponding to refusing service, a form of denial of service attacks. These attacks cannot be prevented as long as untrusted commodity OS has access to platform resources such as storage or network. Although FTPM system the paper presented will remain secure in the face of these attacks, the malicious OS could starve the FTPM, leaving it inaccessible. In addition, the FTPM system do not defend against power analysis or other side of channel attacks that require physical access to hardware or hardware modifications. The paper used three approaches to overcome the shortcomings of ARM TrustZone. First, they imposed the additional hardware requirements on device manufacturers to ensure a minimum level of hardware support of the FTPM. Many mobile devices already come equipped with an embedded multimedia controller, eMMC storage controller, that has an off SoC replay protected memory block, the RPMB. The RPMB's presence combined with encryption ensure that TE can offer storage that meets the needs of all the FTPM's security property. Second, they have made some design compromises. They require that no TE code paths can execute for long periods of time. Third, they modify the TPM 2.0 semantics. It is determined that FTPM cannot offer any TPM commands that require a clock for their security. Spencer will talk about
With some of that background, I'm now going to talk about some of the hardware requirements and some of the other design compromises and features that were made in FTPM. So the first, as mentioned earlier, is the embedded multimedia controller, which has the replay protected memory block. This has two different functions. One of them is for generating hash-based message authentication codes with SHA-256 hashing. And the other thing this has is the memory block that provides secure storage, which was one of the TrustZone shortcomings that it's going to overcome. We also have the secure world hardware fuses, which were mentioned earlier. These have a numerical identifier that's described in the paper as difficult to guess, and this is used as a seed for additional RSA secret keys. And this also provides some secure storage to the trusted execution environment. We also need to have a secure entropy source. In discrete trusted platform module units, this is usually some sort of an oscillator or outside generator. But in this, it's seeded with the hardware fuse number. It's required for true random number generation, and it's used in the RSA key creation. Next slide, please. So one of the design compromises that's made is creating RSA keys. The FTPM needs to wait for entropy to accumulate in order to generate the prime numbers. Prime numbers in TPM 2.0 are checked with the Miller-Rabin probabilistic primality test. And this test is repeated 5 times for RSA 1024 and 4 times for any of the larger keys. The likelihood of a number not being prime then with this test is 2 to the negative 100. So it's highly unlikely that you have a prime number that is, or a prime candidate that's not actually a prime number. And then this is to create those secure RSA keys. It also has cooperative checkpointing. So one of the things that was mentioned is that a command cannot run too long on the TPM. This is because the minimal OS in the trusted execution environment doesn't have a preemptive scheduler. And because of this, when you run a process such as creating an RSA key, that's a very lengthy process and that can cause OS functions to starve. Because of this, we have cooperative checkpointing implemented, where anytime a TPM command is taking longer than expected, FTPM will checkpoint its state in memory, and then it will return a special error code to the OS in the normal world. Next slide, please. Some of the other TPM 2.0 specifications that have been included are the secure clock. The secure clock measures lockout durations, which is when a TPM refuses service. This is something that's a necessary implementation because in case there are needed like keys valid for an hour, for example, that's one of the use cases that the secure clock provides. It also measures lockout durations. So that's when the TPM refuses service. And this is in order to prevent a dictionary attack or brute force on the TPM. It needs to make sure that it's able to measure the time so that it can lock it out for that duration of time. And in order to do that, it has to trust the clock. Next slide. One of the important things that the clock is necessary for is these dark periods too. In the figure on the left, you can see that without a dark period, or the dark period is where the FTPM actually does not have external secure storage because the firmware has unloaded its storage drivers and the OS doesn't have storage yet. So this is actually when there's no storage. And you can see that on the left, that's a secure implementation because it has the storage that it's able to access TPM with storage. And after the failed attempts reach 3 times, it's able to enter that lockout period. The figure in the middle is an insecure implementation because when the TPM doesn't have storage, And then it does not have access to the OS storage, and the firmware has unloaded the storage drivers. And in this time, an adversary would be able to brute force the TPM. So this is an insecure implementation. And then finally, on the right, that is the FTPM implementation. So this has the dirty bit, which in TPM 2.0, this has been referred to as the non-orderly or unorderly bit. And what this is able to do is before the dark period is entered, the FTPM sets the dirty bit. If a reboot occurs during the dark period, then the FTPM will enter lockout automatically because it detects that someone is trying to circumvent the methods of or circumvent the dictionary there so that they can guess multiple times, or they're trying to circumvent that. So with that dirty bit, that becomes no longer allowed, and we are able to have a TPM with a dark period that is still secure. Next slide. So now I'm going to talk a little bit about the performance of FTPM and compare this to DTPM, which is a discrete trusted platform module, which is the existing standard. In order to measure the FTPM and see how it measures up to DTPM, they determined the overhead of expensive FTPM commands, such as creating RSA keys, and they measured the overhead of typical commands and how that compares to DTPM. So figure 7 shows the latency of creating the RSA 2048 keys. And you can see that on average, FTPM is faster than DTPM. One of the important bars to look at actually right here is DTPM number 3. And this one was thought to actually search for prime numbers in the background and maintain a cache of prime numbers without any command actually being issued. So that's why that one is actually faster than the other DTPMs and faster than even FTPM2. The figure on the right is the performance of searching for prime numbers. So the TPM module, in order to generate those keys, needs to have a pool of prime numbers. So you can see how long it takes to achieve those candidates with the time on the y-axis and the number of candidate primes on the x-axis. Next slide. And this is a chart of some of the standard TPM commands. Again, what you can see right here is FTPM very much outperforms DTPM greatly. The slowest FTPM on average is 2.4 times faster for decryption, and the slowest FTPM is 15.12 times faster in the seal command than the fastest DPPM. So for every instance of an average command that might be issued, the FTPM outperforms standard TPM. Next slide. So in conclusion, which one is better? It's a little bit hard to say. ARM Trust Zone has a couple limitations that we've shown are able to be mitigated in the FTPM implementation. And FTPM provides a significant performance increase with its standard operations. However, there's a different attack surface with each one. Discrete trusted platform modules are connected to the CPU with a serial bus, and this serial bus is vulnerable to eavesdropping. So that's the one weakness of discrete. But the advantage of that is that is its only weakness, whereas the firmware trusted platform module, it's vulnerable to memory attacks from the DRAM or from side channel attacks. However, it's faster in most computation speeds. DTPM is generally better for servers, is one of the sort of agreed standards, because if a server is hosting multiple users' private data, then it's a little bit more secure to keep those encryption keys on the discrete platform module, whereas FTPM might be better in client implementations because it gives increased speed to the clients. And this technology is actually relevant to today. If you are considering upgrading to Windows 11, then you actually need to have a TPM module in your system. And I know for me, actually, in figuring that out, I had to enable FTPM in my own computer BIOS. So this is actually technology that I believe everyone should be aware of, as this has current day ramifications. That's everything from me, and we're open to any questions that people might have. Thank you.
Great, thank you so much. Any questions, anybody? All right. So that's all right. That's the end of the presentation for today. Certainly there are, I mean, this is a very active area of research. Lots of papers on both on the defense and attacks areas, and of course the major challenge, as I said during the class as well, is kind of finding a scenario where the method is efficient, but on the other hand is also effective against different types of attacks, including fault attacks and side channel attacks and all those things. So that's a very difficult problem to solve, and that's where we are right now to see what we can do. So, yep. Arjun, you have a question?
I had a general question. So when like security researchers find vulnerabilities on like common chips and stuff like that, do they reach out to like Intel or AMD before publishing, or do they publish and then?
Yeah, absolutely. You have to reach out to them before actually publishing. So usually there is this responsible disclosure that you have to follow. And actually, whenever you're sending a paper for review, that's one of the key things that the reviewer will ask, that whether you have reached out or not. And failure to reach out is actually usually automatically rejects your paper. Not only that, you will face some consequences if you don't. So not only you have to, you must actually do it. Otherwise, you'll face some consequences.
Got it.
Yeah, but yeah, definitely. Any sort of vulnerability you find, you'll have to reach out to the responsible people that, you know, either Intel, ARM, or it could be software, or it could be any. So whoever is like kind of official provider of that service, you have to talk to them. Shreyas?
Yeah, just as a follow-up, I was wondering if like there are bounties for even for like hardware securities. So for example, in the Plunderbolt paper, which I guess is a software security issue, but would they also get like a bounty in the case that they disclose it to Intel first? Or is it just like a
Usually
lawsuit?
no, not really. The bounty is typically well, of course, publishing. I mean, usually these things coming out of academia. So the reward is you manage to publish a paper, and usually, especially attacks new vulnerabilities, gets lots of news coverage. So that's usually what you would interested to do. Why you would be interested to do things like that. So the professor and their team, they get, you know, news coverage, get famous in the, you know, area, and so on and so forth, and then citations and so on. So that's usually the what happens afterwards.
Okay.
Was that your question, or your question was something else?
Yeah, I mean, I was trying to think along the lines of why unless it's by law, why would the security researcher want to go and tell the company about it? Because they're sort of getting in some ways like a free security check of their system. So I was just curious
so
about
I mean, yes, ethical reasons you have to disclose it. Otherwise, as I said, usually all the conferences, especially security conferences, if you go and read their website and the call for papers, all of them has this clause saying that you are responsible disclosure. Usually there's some sort of like a deadline and timeline for it as well. And failure to follow those guidelines will result in automatically rejecting your paper. So yeah, so same as like, you know, if you need to, for example, do human related resources and researches, you have to get some documents and get some proof and get some licenses. The same story goes for security as well. Actually, it's like not very long ago, there was this interesting news about a group at University of Minnesota that what they did was they published this paper that they showed that they managed to well, they didn't really do it, but I mean, at least the way that the paper was written was they managed to send some updates to the main branch of Linux kernel, if I remember it correctly. And they kind of like, send some malicious code there and then manage to actually add it to the actual branch. The research was kind of like showing that, how an attacker can do that. And then they were like obviously working on the defense mechanisms. But as part of the paper, they were showing that it's actually doable. The problem was they didn't really, first of all, didn't get permission for doing that, and then also they didn't really notify the people was like handling the repo and so on to that they are doing this. So that was like creating lots of pushbacks, both from the the open source community and from the university itself. So it's actually getting to lots of legal stuff because of that. So if you follow University of Minnesota, let me see if you can find the link and share it with you.
But also, how would they would have no other way to test their theory, right?
Sure. I mean, it is. Let me. Yeah, I think I found it. No, there are ways that you can do it. You don't have to necessarily, fall. Oh yeah, somebody also found it. This is another link. There are ways to do it. First of all, you need permission for doing it, and then you don't need to necessarily put it on the major branch. You can always like create your own branch and do the stuff. So of course this is, I mean, they were arguing that the way they did it, what they were like careful, and they never actually merged it with the original one that people actually download and use. But still, there were lots of pushbacks. I mean, if you follow the stories, you will probably read it. You will understand it. But yeah, the pushbacks was like, first of all, it's like time consuming for people who are working on the actual product to like try to find these and remove this and so on. So there are issues. So for example, if somebody says that, I mean, if we want to test something on security of Bank of America transaction, what we did was messing up with the all the transaction, right? So that doesn't make sense. So that's the same story.
Okay, thank you.
Yep. So let me see. There are some things on chat. Some companies offer bug bounties for finding exploit, but I imagine it's different from academic research versus I mean, there are like many companies actually do have penetration testing, white hackers, and so on. So many of these security, researches and positions that are available in many of these companies are actually actively looking at vulnerabilities and exploits exist in their systems. So that's one thing that they're actually being paid to do that. And then there's also always, hackathons and bounties and things like that companies ask people to do it for them. And then they also fund research, right? So that's also another way of them to support these kind of researches. So for example, if I come up with this idea to Intel and say, okay, what we are looking at, for example, side channel analysis of these, most of the time they actually fund this researchers. So that's the way that it kind of like they provide resources for researchers and academia to do this research for them. Okay, any other questions? All right, so is there any question about the quiz? Anything from previous lectures, anything that people didn't understand? Now it's a good time before the quiz actually to ask those questions. Anybody, anything? So there was also last time I zoom in a little bit. Yeah, we didn't have much time going over the last part of the previous lecture. So last thing we discussed was different things in trusted execution environments, mainly 3 things that we discussed. You now seen like Keystone and how that works, FTPM that works. There are others as well. If you're interested, take a look at them as well. And then one last thing that I didn't really have time to discuss was software and remote attestation. So remember that last time I said that T is basically useful for 2 things. One is when the operating system or generally the system cannot be trusted. And in that way, we use trusted execution environments to kind of like shield and isolate part of the hardware and that is not controlled by the operating system. Another thing that these can be useful for is remote attestations. And we also discuss how we can, share keys and send the data and code in a private manner and so on. But other than, using keys for remote attestation, there are what's called hybrid or software methods in order to enable software attestation and remote attestation. The reasoning for not using keys specifically is that we're looking at more low-end devices, constrained devices that we necessarily don't have access to things like trusted execution environments and so on, right? So in software solutions and hardware solutions, we want to implement a method in order to do remote attestation, but without really relying on the trusted execution environments, right? 2 main challenges. One is because there is no actual hardware that guarantees us that this is actually trusted, we can always check that whether that part of software or that specific record is not modified or not. There are methods for this that we're going to discuss. What we cannot get is that we cannot get guarantee that this execution will be uninterrupted and will always finish to the end, because essentially we can always imagine that we do the test and we get the results of attestation, but since we don't have hardware to enforce that, the operating system, for example, can take over and run something else or pause our execution and do something else and so on. So that's kind of like the trade-off between the 2 scenarios, but it's always useful for having this remote attestation capability in some scenarios, right? And then another challenge is kind of relevant to the first challenge is time of check, time of use, where essentially we check something at time t, but we actually executed at time t plus x. And this x, interval is when the actual attack happens. So if the attack happens between t and t plus x, then there's no way that we can actually find out that the attack has happened, right? So our time of check is t, but the time of use is t plus x, and in between the attack happens. So that's also a very known and very important vulnerability that exists in any of these systems that we're going to use this way. And there's no solutions for it. Of course, the smaller this difference, this time interval gets, the probability of the attack also gets smaller and smaller. So that's why you usually have to be careful of when you're checking your system, the status of your system, and when you're actually wants to run that specific part of software and so on, all right? So what are the solutions? The idea is that instead of relying on the hardware and reserving some part of the hardware, we kind of like, rely on some physical characteristics of the system, right? So what physical characteristics? The main one is time. So basically what happens is we are saying that in order to do the remote attestation, we need to do 2 things, right? We need to do we need to compute the hash function, and we need to compare that hash function with the original hash function. And of course, the attacker can try to mimic the behavior of hash function computation and tries to change the hash function with some valid hash function and then mimic that behavior and forge that value and send that to us, right? So that's the way that the attacker tries to counter this. But if we kind of measure time during this hash function calculation, and we design our system such that if the attacker tries to forge this hash function, it takes significant amount of time, then the time can be a good indicator that whether this process is valid or not. So for example, let's say that if I want to compute the hash function over X blocks of memory, it takes T time. And if the attacker wants to forge this, the attacker has to, incur some additional overheads. Let's say X, right? So in order to mimic that behavior and forge that hash function, the attacker needs to spend T plus X time, whereas we know that the original calculation of the hash only takes T time. So essentially what we do is that we're going to do two things. We're going to send the request for computing the hash. And in addition to that, we're going to start a timer for that request. And we only say that this software has not been modified after two things has been satisfied. One is that the hash function is indeed correct. And the second thing is that the timer, that time is less than T. Otherwise, if either of these two is not correct, then we're going to say that, there's something wrong with the systems. Either there is an attacker that tries to forge, or the attacker has managed to forge and the hash function is not correct, right? And what happens is you can actually rely on other physical characteristics as well. Actually, my team had a paper on this that we showed that, for example, side channel information, like physical characteristics of the signal, can actually be used in order to give us this notion of whether this hash function calculation is running correctly or not. All right. So generally, the idea is that instead of relying on the hardware, let's rely on some physical characteristic, design the system such that if the attacker tries to forge the system, they have to actually incur more overhead for that specific physical characteristic, be it time or side channel or anything else. And using this additional source of information, now the user can actually build a trust on the system. Is there any questions here? All right, so that's the end of the discussion for T's. We talked about how to build T's, why we need T's. We talked about kind of a bunch of different, industry and academia level architectures and standards. And we also talked about remote attestation as one of the key things that T's provide to us. And also sometimes we don't necessarily need T's for getting that. So that's also another thing that we talked about. Next week, we're gonna start talking about memory safety. So next week will be entirely talking about memory safety. And then after that, we're gonna start talking about side channels. So we're gonna start with talking about microarchitectural side channels, things like cache side channel attacks, Spectre and Meltdown. And then we're going to switch to physical side channel attacks, such as electromagnetics and power side channels. And then finally, we're going to finish the topics with cyber physical systems and attacks and defenses in that area. All right. So don't forget about your quiz on Friday. This will be the first quiz. We're going to have another quiz in week 8 or 9. I think it would be probably 9. And as I said before, those of you who don't want to do the project can do the final exam instead of the project. So that will be during the final weeks as well. All right. Any questions? Anybody? All right. So that's it. See you on Monday. All right.